Okay class, welcome back. In this video we're going to spend more time determining and predicting the solubility of different substances. Our objective for this video is two-part. The first is that we'd be able to generally predict whether or not a substance would be soluble in water. And our second part, or our second objective, is that we would be able to mathematically calculate the molar solubility of a substance. And saying that, we have a lot of material to cover, so let's dive in. In our past lectures, if a compound can dissolve in water, then it is considered soluble, while if it does not dissolve in water, it is considered insoluble. So we have said that solubility is the ability for a substance to dissolve. The solubility of a substance is not as concrete as a substance can or cannot dissolve in water. In reality, solubility can be thought of more as a continuum. Even insoluble compounds can have, at some extent, dissolved portions. It might be negligible in comparison to more soluble compounds, but we still had some things or some parts that can dissolve. For example, if we mix silver 1 nitrate in water, it would dissolve and form a strong electrolyte with the silver cations and the nitrate anions. But if we take silver 1 chloride, it basically does not dissolve in water despite having a silver cation and chlorine anion. Though there is no easy way to just look at chemical formulas and determine whether a compound will or will not be soluble, there are some generalized rules in which can help you with a majority of the determining whether a compound you will use in this class is soluble in water or not. The chart that should be on the screen now should give you an idea of what is soluble and what is not soluble. I know it's a lot and it's honestly a pain, but it would be extremely beneficial if you commit this chart to memory. I do not ask you to memorize a lot in this class. This is one of those things I am asking you to memorize. So now let's go through this chart and read it. This chart tells us the solubility of ionic compounds in water. Our first group of compounds are compounds containing the following ions are soluble in water. If they contain the cations of lithium plus, sodium plus, potassium plus, or ammonia plus ions, then they will dissolve in water with no exceptions. If a compound contains either a nitrite anion or an acetate anion, they will also dissolve in water with no exceptions. So, if I have a compound of potassium hydroxide or KOH, it can dissolve into the potassium plus cation and the hydroxide minus anion, which is because the potassium cation can dissolve in water. Going back to our silver 1 nitrate illustration, the reason it's soluble in water is because it can break into Ag plus cations and NO3 minus anions, and according to our rules, NO3 minus is always soluble in water. The next group of anions that we're going to talk about is calcium 1 minus, bromine 1 minus, and iodine 1 minus. If the substance contains any of these anions, they are soluble in water, except when they are paired with silver 1, mercury, or lead 2 cations. So this explains why our silver 1 chloride is insoluble, because despite chlorine minus being soluble in water, the majority of the time it is insoluble when it is paired with silver 1. Our final anion that is soluble in water is a sulfate anion, or SO4 2-. The only time this substance is insoluble in water is when it is paired with strontium, barium, lead 2, silver 1, or calcium cations. So H2SO4 would be soluble in water, but PbSO4 would not be. Our next set of ions are ions that generally are insoluble in water. Our first set of anions they're going to look at are the hydroxide anions and our sulfur 2- anions. Generally, anything paired with these substances are not soluble in water, except for if the following conditions are met. If either of these ions are paired with lithium, sodium, potassium, or ammonia cations, then they're going to be fully soluble in water. If my sulfur 2- is paired with a calcium, strontium, or barium and form a compound, it would be completely soluble in water. If my hydroxide anion is paired with a calcium, strontium, or barium cation, it would be slightly soluble in water. So sodium hydroxide, or NaOH, would be soluble in water, but aluminum hydroxide, AlOH3, is not soluble in water. Our final set of rules are for carbonates and phosphate anions. Generally, these anions are insoluble in water unless they are paired with lithium, sodium, potassium, or ammonium cations. So, now that we have this chart complete, if you want to pause this video and write these down, please do so now. We can better understand the solubility of ionic compounds by applying the concept of equilibrium to the process of dissociation. For example, we can represent the dissociation of calcium fluoride in water as an equilibrium equation. In other words, CaF2 solid is at equilibrium when 1 calcium 2 plus cations is added to 2 fluorine 1 minus anions. The solubility product constant, or Ksp, is the equilibrium expression of a chemical equation or dissociation of ionic compounds. So, using our equilibrium formula from earlier, we can say Ksp equals the concentration of the calcium 2 plus cations times the concentration of my fluorine anions squared. We represent this by putting Ksp equals brackets Ca plus 2 in brackets, start brackets up again, F minus 1 in brackets squared. Notice we did not include the CaF2 solid in the equation. This is because Ksp is the measure of solubility, and our CaF2 is a solid state, not an aqueous state, so it is not dissolved. Your Ksp values will be provided as the following chart in your classwork or given to you on a test. Let's take this a step farther. Let's use Ksp to find molar solubility. Molar solubility is the solubility in units of moles per liter. If we are given Ksp of a reaction and we can determine what its equilibrium equation is, we can solve for molar solubility. So let's take the dissociation of silver 1 chloride. The Ksp value for silver 1 chloride is 1.77 times 10 to the negative 10th power. Its equilibrium equation would be AgCl solid is at equilibrium when 1 aqueous silver cation is added aqueous chlorine anion. Before we go any farther, we need to understand that Ksp is not molar solubility, but the solubility product constant. The solubility product constant only has one value at a given temperature. In order to find molar solubility from Ksp, it involves setting up an equilibrium problem and an ICE table. An ICE table stands for initial, change, and at equilibrium. So, we will set up our ICE table for the concentration of both ions in this reaction. So we would start with silver plus cation and chlorine minus anion at the top. Now we would have our headings. So let's spell out ICE. Remember, ICE is initial, or I is initial, C is change, and E is at equilibrium. We are going to say our initial values before the substance went through its equilibrium reaction is 0 for both our silver and our chlorine, because we have not dissolved any silver chloride in water yet. We are going to let S represent the concentration of silver chloride that is dissolved in water in our molar solubility. In the case of this silver 1 chloride, we are going to use 1 silver cation to 1 chlorine anion. So we just need to put plus S for the change under each of these ions. This gives us 0 plus S equals S for each of our equilibriums. Now, let's plug into our Ksp equation. We know Ksp equals the concentration of silver 1 times the concentration of chlorine 1 minus. So Ksp at equilibrium equals S times S. We can multiply our S's together, and we would get Ksp equals S squared. So, in order to solve for S, we are going to have to undo our S squared by doing the square root of both sides. This is going to give us S equals the square root of Ksp. Now, all we have to do is plug in our Ksp value and get the molar solubility of silver 1 chloride, which is 1.33 times 10 to the negative 5th molar. Because this is such a new topic for you, let's work on one more practice problem before moving on. Calculate the molar solubility of lead 2 chloride in pure water. Well, We always write out what we know first. If we are dissociating lead 2 chloride in water, then we are going to have an equilibrium equation of PbCl2 at equilibrium equals Pb plus 2 plus 2Cl1 minus. Now we can write our Ksp for this reaction, which is 1.17 times 10 to the negative fifth, or in other words, this is our concentration of lead 2 cations times the concentration of chlorine 1 anions squared. Notice the concentration of chlorine is squared. This is because in the formula of lead 2 chloride, there are 2 chlorine atoms for every 1 lead 2 atom. Now that we have this, we can set up our ice table for our equilibrium equation. We have our lead 2 and our chlorine minus as our headings for our table. We then state that our initial amount for each of these ions is 0. Next, we can use the coefficients in our equilibrium equation to determine our S's. So we would put plus S for the change in our lead 2 nitrate or to lead 2 ion, because there's no coefficient in front of it, and 2S for our change in the chlorine anion, because there is a 2 as a coefficient in our equilibrium equation. This gives us our equilibrium S and 2S. Now remember, Ksp is the concentration of lead 2 times the concentration of chlorine squared. So now we plug our S's into the concentration brackets, and we get Ksp equals S times 2S squared. If we follow order of operations, we would then get Ksp equals S times 4S squared, which would result in Ksp equaling 4S cubed. Okay, we're on the home stretch for this one. Now, in order to isolate S by itself, we are going to have to divide Ksp by 4 and then take the cube root of it. So the equation should read S equals the cube root of 1.17 times 10 to the negative fifth over 4. If we plug these in correctly, our calculations would give us the molar concentration is 1.43 times 10 to the negative second molar. Okay, I think I've tortured you enough with this bit of math and solubilities. In this video, we learned how to predict the solubilities of a substance and use mathematical calculations to calculate the molar solubility of a substance. I hope this video helped you out, and keep up the good work in the class. See you next time.